Good afternoon. I'm Alex Russell. I'm a software engineer on the Chrome team. Thanks for tearing yourself away from lunch to come hear about JavaScript. So, like I said, I'm an engineer on the Chrome team. And before I joined Google, I spent a lot of my life working in JavaScript. I joined the Chrome team from a web development background, specifically working on open source JavaScript toolkits. And before that, working web application development and security. And before my recent detour into C++, I spent most of my day trying to figure out how to make JavaScript do interesting things. My personal history with JavaScript started in 1997, I think when a lot of us started to be cognizant of the web. And at the time, JavaScript was this thing that was starting to become powerful and somewhat standardized and somewhat widely available on the back of the browser wars. So I want to talk a lot about how we got to where we are today with JavaScript, why it's so important, why that history, that long history, continues to figure into the sorts of things we try to do with JavaScript on a day-to-day basis. And I want to take you through what's really inside of JavaScript. What is it about JavaScript that makes it so different to the languages that you might be using in your day-to-day work that aren't JavaScript? Because there's a lot that is. Exactly where are we right now? Because I think this is also sort of an ambiguous question, right? If you're a browser vendor, it's easy to say we're this fast, easy-ish. If you're a web developer, you can look at your deployed base and understand who's got what, but that doesn't necessarily tell you anything about the future. And I want to spend a lot of time today talking about how it is that we are going to get a different future for JavaScript, because JavaScript, like the browsers, is starting to move again. And I want to tear back the veil that covers each of these topics and help you understand exactly what's going on and how these parts relate to each other, because they do. The history informs the future, and the current state informs what's going to happen next. So JavaScript is a functional language. So how many of you write in other functional languages or are familiar with functional languages? Awesome. The front of this talk is going to be something that maybe just warms your heart and may not be new information. So JavaScript is a functional language. In the sort of the history of functional languages, it supports closures. Much like Scheme, it's got this nice first-class function system. And in 1995, Brendan Eich hacked it up as a little prototype, which made its way into Netscape 2. And Netscape 2 was the first browser to really have any serious scripting support. It had DOM level 0, and soon afterwards, JavaScript sort of, once it escaped into the browser, started the standards process at ECMA, not inside the W3C, because the W3C wasn't a place for languages. And in 1997, we got the first version of JavaScript as a standard. In 1996, Microsoft shipped IE 3.0, and that was the first version of JScript. So we now had two competing, mostly compatible implementations of a scripting language for the web. Nobody knew how big the web was going to be, although at the time it looked like things were trending up. Well, we know how that story ends. Today, you can't ship a credible platform that doesn't have the web. In 1999, ECMAScript version 3 was finalized at TC39, which is the technical committee that is the standards body for JavaScript. And from its humble roots as Mocha/LiveScript/JavaScript in Netscape 2, JavaScript 3, ECMAScript 262-3, the version of the standard that was released in 1999, has powered us pretty much to today. It has been the thing that for more than a decade has been what we think of as JavaScript. And JavaScript, on the back of that standard, has gone pretty much everywhere. JScript, the component that runs JavaScript inside of IE, has been built into the OS for Windows since Windows 98. You can't get a copy of Windows, you can't buy a copy of Windows today that does not include JavaScript in the OS. And every browser on the planet now includes at least one implementation of JavaScript. And these things are moving really, really fast. I work on the Chrome team. Therefore, I'm partial to V8. It goes nice and quickly. But these things are all compatible to a very high degree. All of these implementations are separate implementations, and they're competing on things that aren't, oh, here's a new language feature. We're collaborating on language features in the standards committee, but we're competing on performance, which is a really great place to be for a language, because it takes a lot of investment to make a language a real success. It takes a lot of deployment, a lot of competition, and a lot of investment to sort of get the really smart guys that it takes to go make a VM go like hell. And so JavaScript has been the beneficiary of this sort of ecosystem of investment in a way that only a couple of languages before it ever have. And as a result, today's JavaScript runtimes and today's JavaScript performance are vastly different than they have been in the past, even the recent past. And so every device that you get today, including the tablets that were handed out to you yesterday and the Chromebooks that you'll be receiving as attendees on June 15th, these all have JavaScript as a core part of their runtimes, because the web is the platform. The web is the way that you're going to build a lot of the applications that your users are going to care about, and it's the way to build portably today. So JavaScript is everywhere, and it's terribly misunderstood. And I think what I want to do first here is to talk you through the parts that most people don't really have a sense of when they talk about like, what is it that makes JavaScript different? Because we hear it's a dynamic language, we hear it's a functional language, but it looks a lot like C, it looks a lot like Java, it looks like a lot like C++. And some folks have been doing a great job in the last couple of years of sort of helping to tear back the blinders that are on us as folks who come from a C or C++ background and help lay out what it is. But I want to go through it very briefly, because I think it's important to understand what's actually in there, because when we understand what's actually in there, we'll understand how the language can evolve, because you don't want necessarily separate competing ideas to be existing inside the same language. You want a language to sort of have a theory of itself. You want it to be coherent in ways that make it so that when you understand one part of the language, you can understand the next part of it. And my interest in this is coming from a background as a web developer. I serve as one of Google's representatives to TC39, the Standards Committee for JavaScript. And so I have a particular and keen interest in making sure that we evolve the language in ways that are reasonable and solve real-world problems that we've all got. So JavaScript only has a couple of key languages. I said earlier that JavaScript is a little functional language, and JavaScript started out as a very small language indeed. There aren't a lot of core concepts. There's no type system per se. There are types. You can have a number or an object or an array, but there's no type testing. There's no way to define your own types necessarily and have them participate at like function call time and have the system throw an exception for you unless you do the testing yourself. And JavaScript reads top to bottom. JavaScript has run-to-completion semantics. That means that if you start a body of code, there's no multi-threading in the language. There's no way for you to sort of fork off some other process. Anything that does that in a JavaScript environment is doing it as a bolt-on. So browsers with their set timeout and their set interval, that's all happening outside of the core language semantics. JavaScript reads top to the bottom, and the interpreter and runtimes read it exactly and run it exactly that way. If you see a block of JavaScript code, it goes from top to bottom, and that'll become important as we see in just a minute. Almost everything in JavaScript is mutable. That means that you can change nearly everything. And we'll talk about the several exemptions to this rule, but those exemptions are very small and they're very narrow, but they wind up being powerful. So that means that if you get an object back from some function call, you can probably change it in JavaScript. Closure is the way we do private state, though. So if I get an object and everything is mutable, it means, I might be able to surprise somebody else. I might be able to go change some state out from underneath them. The thing that returned me the object might expect it back in some reasonably OK state. Well, the way we do data hiding in JavaScript isn't through the private keyword or through some method that gives you some sort of a private field that you can only see. Instead, we invert the relationship between classes and functions, and we treat functions as behavior that can carry data versus classes, which are data that can carry behavior. And so the last key concept is, instead of having a class as you understand it in other languages, we have prototypes, which is to say we don't have this strong is-a relationship through a hierarchy of classes. Instead, we say, when I don't find it here, please look over there. It's delegation, and it's a one link chain delegation up to a root object that everybody shares. So we'll talk a lot about how exactly all this works, how it fits together, and hopefully you'll understand at the end how it's going to inform where we can go from here. I said earlier that JavaScript runs top to bottom. That means if I see a piece of code in JavaScript, one line before the next, because there isn't necessarily a compile cycle, most JavaScript runtimes traditionally were interpreters. That means that the easiest way to think about your JavaScript program is as something that is going to happen in a live environment. So if you had a command line and you started typing in commands, JavaScript runs almost exactly the same way. Top to bottom, line for line, it gets evaluated in the order that it is written out in the program, more or less. And so statement to statement, your program state can change in ways that are surprising in other languages, where you might otherwise have compile time exceptions. JavaScript just sort of merrily goes on and runs the next line. So whenever we read some JavaScript code, it's important to think about it simply as running at the top and going to the bottom. It's not really some big magical machine that's going to be out there doing something for you, and then it's going to start running your program. It's just running top to bottom. So when you evaluate JavaScript code and you're trying to figure out what's going on, remember that the line before it may be the thing that caused the problem. And JavaScript is functional and object-based. It's really important to think of functions as first class in JavaScript. That means that they're not simply a pointer out in the world that you invoke against something. They are actual objects. I'm going to refer to them through this talk as function objects, because function objects are indeed objects that you can go and hang behavior off of. But you don't hang behavior off of them by extending their public API area. You don't say, I've got a function object, I'm going to add some new property to it. Most of the time, you do that by using functions as scopes. The only way to create a new scope in JavaScript is to invoke a function. When you invoke a function, it sort of creates a new scope. If statements, while statements, for-in statements, those things don't create scopes. Only functions do. So we have this problem of how do we do data hiding? Well, these scopes are really smart, because these scopes hold on to the variables that have been defined above them in another scope. So what we've got here is a function called getCounter. And getCounter defines a local variable I, and it returns another function. And that function references the variable I inside of it. In other languages, like C++ or Java, you really can't do anything here, because that variable I is going to go out of scope in the returned function. We're allocating a new function here, but that inner function is going to hold on to I. It actually allocates private memory to store a reference to I on the function object that's returned out of this statement here. It, again, inverts the relationship. It's not storage with behavior. It's behavior that has hidden storage. And so the way we do private variables and the way we do data hiding in JavaScript is to use this idea of a closure, something that encloses its lexical scope and holds on to variables as a way of passing behavior around. So we can call the getCounter function. It hands us back a function object. We can call it multiple times, and that state isn't gone. We can still see the variable I from inside the outside one, but it isn't referenceable. We can't go and inspect some property on that function object and find out which variables it's holding references to. It gets GC'd just like everything else in the language. So these are first-class functions. These are functions that are things in the system. They're actually objects. You can create them. You can add properties to them. They can enclose scope. They're not simply inert bodies of code that get run. They're participants in the object model. They're participants in the storage system. You can use them, and they're the fundamental concept that underpins a lot of the patterns that we're going to see later. So these functions work together with a lot of other sort of functional ideas about how a programming language can be structured. In JavaScript, we have a filter, map, reduce, and for each method on the array prototype, which means that every array in the system has these methods, which means that instead of having an external iterator, you have an internal iterator. You have something that can call a function across some set of arguments. And so you wind up creating a stack of stuff that you'd like to do in terms of behavior. Instead of passing data structures around and around and around, you pass in arguments to functions and then sort of unwind the thing that you were trying to get done. You express your program's intent in the form of nested functions that are going to unwind to some result, not linear code that's going to be executed by passing in the same data structures over and over and over again. So these sorts of things are not hard and fast rules about any programming language. Like, you can have an endless debate about what makes something a functional programming language. Can it have side effects? Can it not have side effects? You know, how completely does it support some particular set of macro languages or hygienic macros or whatever it is? Many people define functional languages differently. But for the intents and purposes here, we're just going to say it has closures, first-class functions, and some concept of using those sorts of things to compose behavior nicely together. So another important thing to remember about JavaScript is that everything is just an object. So there aren't a lot of key concepts in JavaScript, and so you can think of it as sort of a lazy language design. It doesn't really have a lot of specialized, compartmentalized things to hold on to different concepts that you might encounter. Instead, it just relies on the same systems over and over again. One of those systems is this small type system, where objects are objects. That first object literal there, it's an instance of object. Arrays are objects, which means that arrays are instances of objects too. And functions are also objects. In this case, I've got a paren here, which is going to create a new expression. I've got a function, which I define inside of here. It doesn't have a name. It's an anonymous function. You can have anonymous functions in JavaScript. And the result of this expression is just going to be that function object. And that function object also is an instance of the object type, which means that nearly everything in the system that you encounter is going to be an object. But this is really powerful because it means, as we'll see later, when we can compose things and everything is mutable, we can start to change the behavior of large parts of the system all at once. And every object in the system acts more or less like a map. There's no separate map type in JavaScript. So if you want a map, just take an object. This is where JSON comes from, this object literal syntax that we've got here where we're defining an object with a single property and a single value. Allows us to dereference properties the same way. So the dot operator does almost exactly the same thing as this map operator. It just finds a property by its name and returns it out the other side. So in JavaScript, everything's an object. Objects operate like maps. That's pretty cool. Arrays do exactly the same thing. And arrays are very confusing when you start out working in JavaScript because you think array is some separate thing over on the side. Arrays are not objects. Arrays are this linear bag of memory that you're going to access with an integer someplace, and as a result of that, you're not going to be surprised by some other identity. But you are, because very often what happens is you go and extend an object. You add a new property to it. In this case, we're going to add this other greeting property to an object dynamically, and to an array dynamically. And as a result, when we go into a for-in loop, this is now an enumerable property on this array. We might get surprised because we see these other things showing up in our object. Well, that's weird. I mean, we iterated over the public properties. Isn't 0 just an integer index thing? It's not a public property, right? Well, remember that everything in JavaScript just sort of falls back on these core concepts. And if you think about the array integer indexing working exactly the same way that property indexing does, it all makes sense. Yeah, in the implementation, there might be some special machinery to make arrays efficient or to pack them tightly so that you don't wind up slowing things down unnecessarily. But in the language semantics, what happens here when I say, please give me item 0 out of this list, is that it turns that 0 into a string and then does a map lookup. That's all it does. So the only magical thing about arrays versus any other kind of object in the system is that when I push onto an array or I set the length property, it actually affects which properties are visible. The length property is the only thing in an array that's actually magic. It has a little bit of syntax for defining arrays naturally. But other than that, arrays are just objects. Things get turned into strings and then dereferenced that way. The spec is pretty clear about this. So JavaScript doesn't have that many core concepts. And if you understand them, you can understand what's going on in your system. So we've got mutable objects. We've got closures, which are behavior that carries data and not data that carries behavior. We've got mutable objects. And we've got everything being an object, and everything being an object also being a map. OK, that's not a lot of concepts so far for a programming language. And we can use these to build some really powerful stuff. So I mentioned mutability, and I said everything is mutable. Just a really quick example. We can add new properties at runtime to every object. Remember how I said that JavaScript runs top to bottom? When you're reading a program like this, it's not like my object type somehow was extended, and therefore every object of this type is going to have one of these properties. I'm just adding a new property to the object directly. So in this case, object.item is being replaced, and object.item2 is simply being added. These are exactly the same operations as far as JavaScript is concerned. The dot operator just finds you the object and then assigns to it. That's all it's doing. Every object in the system is extensible. Most of them are mutable. Most of the values are mutable, and we run top to bottom. So that means that when I come down here and I delete a property off of the object, the very next line isn't going to see it. But if I had said console.log object.item one line above, it would see it there. This is not a compile time thing. It's just doing what you said, line after line, statement after statement, expression after expression. It seems really simple. It seems pretty obvious. But very few programming languages that you might be using in a compiled environment work this way. So I mentioned that closures are the other side of classes, whereas classes are sort of a nice way of saying, here's a structure of data. I'm going to associate some properties with them, and maybe they'll have some type behavior as well. In this case, we're going to create something that we would call a class in JavaScript. We know it's a class because it's got an uppercase B for the name. This is not a language-enforced semantic. JavaScript doesn't necessarily have classes today. This is just a convention. And as we'll see, conventions figure large into day-to-day JavaScript programming. So remember, every object is mutable. So we're going to create, down here, we're going to create a new instance of our behavior class. We're going to extend the local object, this dot, with the variable that was passed in, the configuration. And then we're going to extend the object again with a function called doIt. In this case, when I call the doIt method of my behavior instance, it's then going to run through, and it's going to say this.config and go grab some flag off the configuration. OK, so we stored some property and some behavior on the object. This looks a lot like what you might expect out of another object-oriented language. The declaration syntax is a little bit funky, but you sort of understand it, right? I've added a method. I've added some data. The data operates on the local object's method. Sweet. Or other way around. Strike that. Reverse it. New behavior, pass in a flag, going to call it false. I get a behavior object, and now I can call a method that uses that behavior, right? So it's going to look at the local object, this, for the configuration, and it may change its behavior based on that configuration. I pass in some other value to it. Make sense? Cool? All right. So this is maybe a little bit more idiomatic for JavaScript. It's the flip side of that. Instead of creating a class that I create an instance of, I'm going to create a generator that's going to pass me back a function object, which is going to hold on to the state. I'm not going to go create a class for it. I'm going to create a behavior generator. You can think of them doing the same thing, just the flip side of it. So instead of saying new behavior, I'm going to say bind me a behavior, which when I call this, note the lack of the new keyword here, I'm going to pass in a configuration. Like we saw earlier, I'm going to pass back out a function object. This is a new function object. Every time I call this method, bind behavior, it's going to pass me back out a new function object. So I'm actually having a new function object allocated here. And that function object is going to have, again, some private storage. And that private storage is going to hold on to the config variable that was passed into the outer function, right? Because each one of these is a new scope, and because scopes can hold on to the variables that they were able to see when they were defined, the function object that gets passed out of here now has a reference. It's holding on to that local state. In this case, it's going to be the object that was passed in. This might go out of scope here, every other place in my program. I may not be able to get a reference back to this object, but my behavior, the B variable that was passed back out, will have access to that data because it's being held onto internally. It's not going to be garbage collected out from underneath me. Closures are the way to invert the way you think about your programs. You don't create classes that are state with behavior attached. You create behavior that holds onto the state that it needs. And you can pass that behavior around because functions are first class. So I mentioned earlier that the last sort of big conceit in the language is that we don't have a way of saying, hey, here's a class of stuff. Instead, we say, if you don't find it here, don't look at my chain of class inheritance. Instead, just go look at that other object. Remember how I said over and over again that JavaScript just reads top to bottom? I get some code. The thing executes front to back, top to bottom. We're going to see the exact same thing here, because what happens every time you call the dot operator is exactly the same thing. I'm going to create some variable that I'm going to call my delegate. It's an object. It's got a single property. OK, cool. There's a new ECMAScript 5 method called object.create. There's other ways to do this in older versions, but they're a little bit mind-bending, and we won't go over them. But object.create, the easiest way to think of it is that it creates a new object, which will look at the object that you pass as its first property. If you don't find a value with the same property name on that object. So let's say, in this case, I'm going to create object2 and have my delegate be the delegate. And so when I reference a property out of object2, it's going to go look it up dynamically. And if it doesn't find it on object2 directly, it's going to go look it up off of the delegated to object. It's going to go dynamically go and try and find it over there. Well, we created another object. In this case, we're setting a local property on that object, whose name is item, whose value is value. And that means that when I look it up at runtime directly, top to bottom, left to right, what I see is that I don't get the value that was set on my delegate. I get the value that was on the local object. The dot operator doesn't fail on the local lookup. It finds it on the local object. And instead of looking up the chain, it says, okay, I'll just give you this object's value right back. So JavaScript is incredibly dynamic when it comes even to looking up properties on objects. There's not some fixed list of stuff that you can do. You can change the delegation, and you can change the properties that are available on every object that you're delegating to, or your local object, and that changes what happens when you go and look stuff up at the very next line. So in this case, if I go and I change the value on the delegate, I change the item value on the delegate. Remember that object2 doesn't have a local property called item. If I fail on that lookup on object2, it just goes and says, OK, let's go consult my delegate. And that delegate is now going to have the new value. So the new value has been shadowed all the way through to everything else in the system that is delegating to that object. This is incredibly powerful. The dynamic nature of JavaScript means that because it reads top to bottom, because almost everything is mutable, and because I can delegate to most other objects when I create something, I wind up in a place where I can create brand new behavior at runtime. I can compose things on the next line that didn't exist before, or I can change the behavior of other objects in the system based on what they're delegating to. This turns out to be a great way to go build up a lot of the constructs that we get in other languages for ourselves, because JavaScript may not give them to us naturally. This power is the sort of thing that really drew me to JavaScript as a young programmer. I didn't really understand what I was dealing with. I remember I had a friend who told me after I'd written some article about how to do signals and slots, some sort of aspect-oriented event style thing. He's like, well, why didn't you just use a closure for that? And it took me a long time, probably 6 months or more after that, to sort of really understand what it was that he meant when he said just use a closure for that. I didn't understand that you could hide data inside of functions. I didn't understand that JavaScript sort of ran top to bottom. But these core concepts allow you to create all sorts of really powerful stuff, assuming we understand what happens with the word this. So the word this is really special. Because we don't have classes that wire up this inheritance hierarchy, and because we're always delegating at runtime, right? Every dot operator sort of does the dynamic lookup on the local object, looks at its delegate, looks at its delegates. The this object is a way of saying, OK, whatever scope I'm in, execute the next lookup against the local object, which means that the this keyword in any function isn't pointing at some fixed object. It's not fixed when I necessarily say, create me an object. It's promiscuous. The this keyword points at whatever object my function is being called through. Right? Remember, function objects are first class. They don't actually sort of carry around relationships to their class or the thing that they were defined in. They hold their own data. So the this keyword is a nice little syntactic out, which lets you say, OK, whenever I look up a property, which happens to be a function, and I call it, the dot operator for method calls says, don't just return it, but if I evaluate it directly, use the dot call property of the function object that's returned and call it in the scope of the object on the left-hand side of the dot operator. I know this is a little bit maybe tricky, but the easiest way to think about this is that in order to wire up this behavior correctly so that it sort of does what you expect out of other languages, we rely on the function being first class, meaning it has its own call and apply methods. You don't say necessarily, hey, function, you're not going to work if you're not called inside of some other object. I can call any function in the scope of any other object. I can assign a function to any other object and then call it through that object dynamically, right? Everything's mutable. Functions are first class. Why not? So in order to get that to execute against the right object, you use the this keyword to go grab the value out of the thing that was on the left-hand side of dot, which is exactly the same thing as saying, please call my function, which I pulled out of that object, in the scope of the object on the left-hand side. Cool? All right. OK. So all this fits together in ways that allow us to recreate a lot of the stuff that we expected in other languages. A lot of this is convention. A lot of this isn't necessarily the sort of thing that you're going to have language level or syntactic support for. But if you understand what's going on there, those sort of core little ideas about mutability, scope, functions as first-class citizens, and dynamic behavior, we can start to recreate things like classes. So here we've got an item type, which is we're going to think of as a class. It's not really called a class. It's just a function. It's got the word function. As we saw earlier, when you use the word new in front of any function, it sort of creates an object, calls that function inside the context of that object, and then returns that object back to you. That's the way to think about the new keyword. So we're just going to create a function, which we're going to call with new sometime later. And inside of it, we're going to execute a couple of other functions. Now, we just saw .call, and .call calls those other functions in the scope of the object that we're being executed in, or that we want to pass in. In this case, we're going to pass in the local object. And we're going to do it twice, which means that inside of tracked, we're going to assign a new property to this, which is to say the object that was passed in. And inside of logged, we're going to assign a new method, where that method is going to go dynamically look up the ID and log it out. So we call these mixins. These two methods up here were written in a way that they don't delegate to anything else. They don't assume anything about the behavior of their methods or the properties that they define. And instead, they just add stuff. They just add stuff dynamically when they're invoked against some other object. So I could call them in any other context, but in this case, I can use them in the item type constructor to extend the item type with some new stuff. We saw earlier how delegation allows you to create new delegate relationships between things, and functions also have this idea of a prototype. This is the exposed version of the thing we saw before with object.create, where I can say, please wire up this relationship so that this object, when you don't find it here, looks at that thing over there. So if we create a new item type, what we'll see is that it has an ID and it has a type associated with property added to them, which is pretty good. And if we create another one, the counter is incremented and the type is still assigned to the same value. But if we create a new sub-item type, what we see is that because the prototype created a new property called type with a new value, again, the delegate system faults on the local object, looks at the object's prototype, in this case, sub-item type.prototype, pulls it out of there, and doesn't fault all the way through to item type.prototype. So we can compose these things together in a way that gives us something like classical inheritance. It's not exactly the same thing. All this is dynamic. I can go and change these prototypes. I can change these objects later. But I've got the ability to factor out code into something like a macro or a trait using mixins. And I've got the ability to create an entire subclass relationship where I define new function types which defer to their superclasses for a lot of their behavior. All right. We're starting to get someplace. These core concepts have given us the ability to define things that the language didn't give us naturally, but we can go get for ourselves. And you know how I said that everything is mutable, more or less? That means that we can go and extend the stuff that is deferred to by almost every object in the system, right? Remember, arrays are objects are objects, functions are objects. Well, those things have prototypes too. They have exposed objects which they defer to when you don't find a property in the local object. So array.prototype is, again, an object which is mutable, and every instance of array, every array in the system that faults on some property is going to go look it up off of this object instead. So I can extend it. I can say array.prototype.clear is a new function. I can extend every single array in the system at runtime because the next line is going to look it up through exactly the same mechanism as everything else, right? This is not me changing the type of array. I'm just extending it dynamically. I'm creating a new thing for you to hit when you don't find the property in the local array object. And I'm going to add two. In this case, they're going to return new arrays when they're done, and so I can chain them together. And so this is how you can sort of create little dynamic languages in JavaScript. You can create DSLs in JavaScript by changing the things that you delegate to. If you create new objects and they delegate to some prototype, and you can mutate that prototype, well, then you can change almost everything about the system. Yes, you can change almost everything about the system. And yes, it is a huge maintainability nightmare. This is really good when your code can do it. This can be a huge problem when everybody's code can do it, especially as you get into larger code bases. So collectively, as a community, the JavaScript world has started to learn these patterns of practice, which they say, please don't ever go and mutate array.prototype. Please don't change object.prototype. So that you don't wind up stepping on somebody else's toes, stepping on somebody else's extensions. But this is power that we'd really like to have. This is power that we'd really like to be able to take advantage of. Being able to extend methods in the system is the sort of thing that we've seen work pretty well in languages like C#, where they have extension methods to interfaces. We really want to be able to use this because it shortens up our code. It makes it dynamic. It makes it easy to read. And it makes it possible to build up the language to meet us halfway, which is a great feature of many dynamic languages. So JavaScript has this incredible dynamic behavior, which gives us a lot of power. And so we wind up using it to do all sorts of things that the language doesn't necessarily, because it's a little language, have built-in support for. So in this case, I'm going to, again, create an expression that has an anonymous function defined inside of it. But instead, I'm going to do some stuff here where I'm going to define a local object, right? We've seen this before. That might get captured in enclosure. And in fact, it's going to here. But the little piece of sophistry at the bottom there, or in the middle there, where I end the function, I end the expression, which is going to return that function as the result of that expression, and that I invoke it immediately, means that what happens here is that I've sort of created some code and just run it directly. I've just top to bottom run some code which is going to define a local variable, create a function, which is not local, which is going to get exported back out to the global scope. But that function can see the local stuff, right? So I can sort of hide away my own private stuff inside of my module by putting it in this pattern, using var for the stuff that's a local, and omitting var for the stuff that's a global. That's pretty good. We've got some sense of modularity, again, built on these few set of prototypical properties of the language: mutability, functions as first class, and functions as the only things that create scope, the ability to modify nearly everything, and closures as a way to bind behavior to data and not the other way around. OK, so as you can imagine, we've seen a couple of places here now with classes and now with modules where we can start to use these patterns together to start to build up our little library of stuff to help us meet the challenges that we've got in a large code base. And in fact, nearly every large code base has a library like this. The world of JavaScript libraries has a lot of different answers to a lot of the questions that you want. So for modularity, it'd be great if we could sort of have a script loader that would pull in a bunch of stuff. It would do transitive dependency management, and it would put our stuff inside of this body of code that we could then think of as something that has dependencies but can also hide local state. So this is the closure example. This is the tree control, and these are its dependencies. And it does almost exactly this, right? This is the module that it might define, and it's going to export some stuff. OK, that's pretty good. But then you look at other JavaScript libraries, and they do almost exactly the same thing. Here's a tree control from the toolkit that I used to work on, Digit. And so that does exactly the same thing, right? We've got this module pattern here where that's going to be what you define inside of it. And at the same time, these two syntaxes and these two semantics aren't interoperable. You can't use them together. That's not great. We're in a place where we have all of this raw power, and we can start to harness it in ways that solve our problems. But we can't say the same thing unless we all agree a priori which sort of patterns we're going to use and in which style we're going to use them. So this is the role of the language. This is where language evolution can really start to pay off some big dividends. And so this is Dave Herman's simple module proposal syntax. And this is something like the array, the tree control requirements written out in the new syntax. As you can see, we actually have syntax for saying this thing is going to be a module. I'd like you to require it. I'd like you to import these sets of things into my local scope. And because we've got syntax for this, in Harmony, which is the next version of ECMAScript, we've got the ability for everyone to agree on what it is you're trying to get done. Because you have syntax, no one now has the incentive to go write their own thing. You can start to rely on there being one canonical way of saying, here are my exports, here are my imports, here's how it's done. And so toolkits can start to interoperate. They don't have to continue to compete or reinvent on the basis of a low-level set of things that you might hope would be provided for you in the language. The same thing goes for classes. You know how we saw all that boilerplate earlier where you had the mixins, which were functions, and the classes, which were defined as functions? Well, they all have the same word, function. How do you know what's a function? Or again, we saw the word function reused to go define that closure, which gave us the scope for using a module pattern. Well, the word function gets a lot of use, and in fact, it is used so often that it's hard to understand exactly what it is you're reading sometimes if you're not familiar with all of these patterns. And so nearly every toolkit comes along and creates a shorthand to help you define a class, because you can just write a function that'll do it. Closure does it. Prototype does it. You can imagine that MochiKit or Dojo all do it slightly differently. And these all lead to slightly different semantics, because the way that you wire up those relationships internally, and I showed you one way with using traits or mixins inside of the constructor functions, they make different decisions. You can compose this stuff a lot of different ways because you're always sort of cobbling it together from the raw material that's already in front of you. It's incredibly powerful, but with that power comes the requirement that you have to get a bunch of people to agree with you about how to use it. And in this case, a bunch of well-meaning library authors came up with really good solutions that fit their constraints. And in this case, they all differ a little bit in terms of the underlying semantic. And that's a little bit frustrating when you want to just share a little bit of code with somebody over there. So what we'd like to do is say what we mean. So this is a little bit of code that comes from Marcin Wishari's awesome Pac-Man demo. But this wouldn't be how you'd write it today. This is how you'd have to write it in the future. Or this isn't how you would have to write it today. This is what you would like to be writing. You'd like to say, I've got a class. It's got a constructor body. And it's got some methods. And then I've got a subclass, which wires up that prototypal relationship with the other thing. It's got a constructor body, and it defines some properties on its prototype. What we'd like to do is have this syntax map to exactly what we saw before, right? We don't want to change the fundamental idea of what the language is. Prototype-based, functions as first class, closures to carry state, top-to-bottom evaluation, delegation and not classes. When we introduce a syntax for the word class, right? What we'd like for this to have happen here is when we evolve the language, we want to hold on to that fundamental set of things that define JavaScript as JavaScript so that you can understand old code in the context of new code, and that JavaScript can maintain a lot of that dynamicness, which pays off so well when we need to start doing things that the language doesn't provide for us. Because what we've seen today is that we've put together a whole series of things from raw parts, just little raw material, things that are very high level constructs that you're going to need to use that you might not expect to be there in JavaScript, but JavaScript provides them for you, and it's easy to love a language that gives you that kind of power. So what we want is something that we in the standards committee call desugaring. And desugaring is the concept of when you define a new idea, or when you define new syntax or a new semantic in the language, it would be best if we could describe that new thing in terms of the stuff that's already there. So if I describe a new language feature by what it would be like if I'd just written it all out, we can start to say, aha, this fits or this doesn't fit with the way we start to use JavaScript today. So this is an example of what I'd like to write in the new style, and what you would have to write today to go make this all work in the old style. OK, that's a lot. And it's a lot of boilerplate that we shouldn't have to write. The same thing goes for a lot of sort of little syntactic niggles. So let's say I want a function that takes variable arguments. Today in JavaScript, I have to go unpack those arguments out of an explicit arguments property that's available inside the scope of any function. So if I want a default value, I have to go provide it for myself. And if I want to go grab variable arity arguments, I have to go turn the rest of the arguments into an array using array.prototype.slice. Pass in the arguments object as the scope, and then say, give me everything after the first one, right? And then create me the list of parameters. That's a lot of boilerplate. It's sort of hard to read that function if you don't know this particular sort of pattern, and then to understand what it is it's trying to do. It's much better as a language if what we get to is a place where we can say what we mean when we're writing our functions. I'd like the format to have a default property of blank string. And I'd like the parameters that you don't have allocated to some named argument stashed away in an array called params. Right? That's a pretty common thing to want to do. And so this sort of thing is coming in the next version of the language. And last week at JSConf, and again at NodeConf, we started talking about some work that we're doing on the Chrome team with a JavaScript to JavaScript compiler written in JavaScript called Tresor. And Tresor's goal is to help us design these new language features in a way that works really well by trying them out. Because language evolution isn't a straight line thing. You know, we said that all these libraries have different ways of doing a lot of this stuff. So what we'd like to do is figure out what's the best pattern of practice? What's the thing that we would really like to bless? Or when there is a new semantic that we can introduce into the language, what is it that we would be trying to say in JavaScript directly? And so this way, we sort of have a way of, at runtime, running this compiler over some piece of JavaScript written in the new syntax and have it do something in the old syntax. So in this case, I'm going to go grab something out of the parameters. And as you can see, it's recompiling here as I type. And now it has, yes, there we are. Now it's created all of the stuff that I was going to have to write out by hand. It's just compiled that down from the new syntax to the old syntax, and I can run it. I should be able to run it. Yes, good call. Great, there we go. So This is a tool that we're starting to use to help inform the language evolution in order to help us prototype stuff fast, get feedback about how it works, and so we can start to understand how the new stuff that we're adding into the language fits with the old stuff by writing real code in it. And as we work in the standards committee to help make this stuff reality, this sort of tool, I hope, is going to make it possible for us to evolve faster and evolve in a straighter line with the existing versions of JavaScript. Because what we don't want is for us to add new things like the idea of a class and have it be at war with the idea of prototypal inheritance or functions as first-class objects. We want to continue to help you build on these core fundamental, really powerful building blocks in the language without introducing new sorts of ideas or overhead that you have to consider when you're writing your code. And so Tresor, again, is an effort to help us understand and experiment with a language. And it's available as an open source project on Google Code. You can use it today, both on the server and on the client. And you can start to play with it. You can start to write real code in it. There's a read, evaluate, and print loop that you can just go to and start typing code into. So I won't belabor that anymore. But what we're really hoping for is that you can start to use a lot of the new features that we've started to play with. We have a list of features that we've implemented in Tresor, and that's expanding every day. But things like modules, classes and traits, asynchronous programming. Asynchronous programming is something we have to do all the time, and we wind up doing it with a callback system. It'd be great if there was support for that in the language so that we didn't have to continue to write the same boilerplate over and over and over again. Destructuring assignment, like we just saw. And the ability to use the prototypal sort of style of extension, but have it happen in a way that doesn't conflict with everybody else's objects in the system. Those are the sorts of high priority items, work items that we're starting to use Tresor to evaluate designs for. And we'd love your help. We'd love for you to start using it, testing it out, working with the system, and helping us write code in the new style so we can understand whether or not it's actually good. So Tresor is one idea to help us get there. We need implementations early to inform the design process for the future of the language so that the things that you do in the language now carry out into the future as core idioms and core concepts that you can rely on there too. But we need those things to eventually trickle down into real live implementations. V8, other JavaScript engines. And we want to make sure that these things are available to you quickly in the fast-moving constituencies. So if you can start to use the stuff in the Chrome Web Store, because almost everyone in the Chrome Web Store gets, or who you can target through the Chrome Web Store, gets the latest version of Chrome within a week. That's really good. We can start to get fast feedback in the language and in the design of the next version of JavaScript based on your feedback about what's working and what's not in ways that we couldn't before. The lead time on a new version of the language has been years, in some cases closer to a decade. And so you can follow along the ECMAScript wiki. I realize this link's a little bit long, but there's a list of accepted proposals for the next version of the language. That's going to be somewhat formalized in the next couple of months. And as that list is locked down, we're going to continue to iterate on those proposals. They're going to get new syntax. Things are going to change there. But the list of things that are in the proposal stage for Harmony are the set of things that we as a committee have agreed to go work on and standardize together. And so Tresor is going to continue to follow that evolution and allow us to start to work in ways that give us quick feedback about whether or not we're doing the right things for you as you're writing large pieces of JavaScript. OK, questions?
Hi, so the CommonJS modules specification has like a really simple require and exports that really does, it doesn't factor in, how things get loaded or whatever. It's really just a binding mechanism between disparate namespaces. That seems ultimately simple to me, but it doesn't seem like Harmony's going in that direction. So
the simple modules proposal gives us a way to have a first pass. So sorry, I should run this backwards. The CommonJS module system sort of is implicitly server.js. You kind of assume that the thing that you're getting in the next statement is cheap to fetch. And so what we need for the client is an ability to make the require and provide statements look apparently synchronous, but have them operate asynchronously on the network, which means that we want to get the transitive closure of all of the dependencies that your module needs. And then
you're kind of mixing like the loading and...
They are mixed. There's no way to unmix them. Because of the way that JavaScript evaluates top to bottom, we either have to, and because it runs on the UI thread, we either have to block the entire client while we go fetch resources, which is what happens with a document.write, that sort of thing.
I see what you're
Or
saying.
we have to find a way to accommodate asynchronous loading in the syntax. And that's what the simple module proposal
I see what
does,
you're saying.
which is fundamentally different because we can use syntax to do that in a way that CommonJS can't.
Yeah, I use a system where I kind of use CommonJS on the client, but I don't. I allow for like forward references,
Right.
so like those things they get resolved at a later time, so you can't kind of use them completely until until later.
I'm really hopeful that we can get the semantic that Dave Herman has put forward, because it really does give us the power to not force you to think about when your code's going to run. If you say require in one line, you can use it in the next one, and I think that's a key usability feature of a language improvement in this area.
A question on the last slide, one of the things you mentioned was asynchronous programming with JavaScript, and like Node.js is one of the new frameworks. Wondering if you can talk a little bit about some best practices for how to handle error conditions or exceptions when you're doing an asynchronous call that may not be in the same call stack as when you actually executed the call.
So this is a hot topic. The asynchronous pattern that seems to have won the most mind share is something like deferreds or promises. Again, the CommonJS guys have done great work there. And so those systems tend to have some error handling callback that you can register so that if an error does occur, you can be notified of it. I actually was talking with the Node.js guys just last week in Portland about exactly how they want to do this, because I'm hopeful that what we can do is build on top of built-in language deferred or promise API, the ability to use the await or async keywords to go help mark particular methods as returning these deferred objects, but error handling does turn into a primary question then. So what they came to, and I think is a pretty good answer, is that you have a single callback, right? And that needs to be also informed of errors, but you can have an optional second callback, which will be told about error conditions if you choose to handle them independently. And I think the idea that you're not going to have to deal with errors in the primary callback is a little bit far-fetched, and so I think that's maybe a good trade-off, but it is an open topic. We probably need language-level support for sort of moving stack traces. Like if I throw in one catch here and then rethrow the exception someplace else, we need some VM or language-level support to help us make that reporting cleaner and nicer. And I think that's another important area where we might be able to help tie these things back together once we go async.
Okay, great.
Hi, I just wanted to know if there was any interest or effort within Google to do some more of the more server-side JavaScript stuff like Node.js, and maybe any possibility of ever having that available like on App Engine.
I can't speak to future product plans, but I can say that the V8 team is working closely with the Node team to continue to make Node faster. We care a lot about their use cases, and we want to make sure that we're supporting them.
So looking at the tracer function and the no sugar desugaring, in Lisp this was done because they had a powerful macro facility, so that a developer could actually introduce new syntax into their programs and define the behaviors in Lisp. Is there any thought in doing something like that in JavaScript?
We have a hard time with that in JavaScript because we have both statements and expressions, and we have a lot of complex grammar that's non-movable. And as a result, any macro facility is going to quickly become undecidable. And so I think we're in a place where macros, the way I think you want them, aren't possible in JavaScript. New syntax specifically is going to have to continue to happen through the committee. So I think there are places where we can carve out some stuff. There's been some good work in string formatting, for instance, to make it possible to plug in through protocols some new behavior into existing syntax. And I think that's maybe the promising way forward.
So did you know that you can build Firefox with support for Python as a scripting language?
I've heard tell of this, but it's been that way for many years, as I recall. So,
yes, debug builds of Firefox come with it. More seriously, what do you think of GWT, or more usefully, Pajamas, as actual development platforms instead of writing direct JavaScript and using the richer type system of Python or Java instead of the bare bones one in JavaScript?
Type systems are really great. I think that it's a key missing feature from JavaScript, specifically because what you wind up writing, again, is a lot of boilerplate to help you test whether or not you were actually tall enough to ride the ride. You actually have to sort of go cart around a lot of this testing magic. I'm not hopeful for type systems. This is my personal opinion. I'm not hopeful for type systems as a be-all and end-all sort of verification system for your program. The web is too dynamic. Client-side programs are too dynamic for that. We're dealing with user behavior a lot. Instead, what I'd like for us to get to is a place where the syntactic warts of JavaScript sort of get eased over one way or the other. Things like CoffeeScript are pointing in a good direction here, where you can sort of come back up with some new syntax, and hopefully that'll eventually work its way into the language. But things like the module loader, they're going to have an analogous API, again, building a protocol that you can plug into with your own code. And that API will allow you to do things like run the CoffeeScript compiler or the Pyjamas compiler across loaded modules before they're run, which means that you can sort of have runtime support for those built in. I think you asked the question of what do I think about those tools as a way to do production work. If your language veers far enough from the core semantics of JavaScript, you wind up not just with the ability to do all sorts of tooling and stuff that comes along with your source language, but you also wind up with the need for the runtime to do dead code addition. You need to go and sort of not just do a one-for-one translation down to the analogous statements in the other language, but you have to make sure that the semantics are right. You have to make sure that you have code in there to support any differences, any impedance mismatches between the two languages. And so I'm much more hopeful about things like CoffeeScript and the Traceur additions because they don't add a lot of extra stuff because the languages aren't that far away in terms of core semantic.
All right, thank you.
Hi, one kind of application domain that could benefit from scripting that's not really, doesn't have a solution today is a native Android app. So I wonder if there were any, we've dabbled with, plugging Rhino in and things like that. I wonder if there's any activity in that area right now.
I think you'd have to ask the Android team. I'm sorry, I'm not up to date on what they're doing there.
Okay.
Thanks.
I had another question. So in my Python programs, I like to use sometimes multiple inheritance, and they have complex
C3MRO, right? Yeah.
dependency graphs and so
Yeah.
on. Yeah. So they have a method resolution order in
Yep.
Python that allows you to call the superclasses methods, exactly once in the right order, and or at least a well-defined order. Is anything going on in Harmony for allowing for something like an MRO type call graph resolution?
I don't think we're going to break the idea of a single prototype. So
Right.
the analogous thing here would be multi-prototype languages. I'm hopeful that what we'll get done is something like Tom Van Cutsum's traits semantic, where we can add a syntax for defining a set of things that you would sort of, like we did with mixins, add to the class, and then do conflict resolution with syntax. Because what you're trying to say in a lot of these cases isn't, I'd like for you to sort of decide for me which of these things I am at runtime. It's not really an
Right.
is a relationship. It's sort
Right.
of a has a relationship where you're saying,
Yeah.
I'd like this new behavior to also be available to my object. And if you can factor those things out, it can help with composability and then eventually with type testing.
Right.
And I think traits are where, at least I'm hopeful that we'll go
Yeah.
to make a lot of that easier.
Yeah, I use a wrapper where like I kind of build a copy of a well-defined prototype chain specifically for this particular set of mix-ins, and so like you can kind of emulate, by specifically listing the order in which you want things to be
Yeah.
resolved, and kind of get the behavior for that in JavaScript. But
Mainly curious, do you know whether Traceur shares common lineage with the cross-interpreter in Google Widget Toolkit?
The Traceur code base is brand new. It's a new client-side compiler that we wrote, hand-built parser, that sort of thing.
Thank you.
Yeah. All right. One more. All right.
So I'm a C# developer, and I've stayed away from JavaScript for a very long time, mostly because I knew the what, but I didn't know the why, and that's been really good in today's session. I'd like to continue exploring. Can you recommend any specific reading material? Because of course I could always do a Google search, but
Yeah.
that would continue along the path of not just the what, but the why also.
The latest version of JavaScript, the definitive guide, is pretty good. I recommend Eloquent JavaScript. It does a great job of sort of introducing these core concepts and getting you through not just sort of what you can do. I didn't talk a lot about how DOM interacts with all of these things. My recommendation is that you find some place to start playing with a language that's not a web browser. I mean, web browsers are really handy. You can start to sort of like make this all happen. But if you just sort of play with the command line in the browser or start to work with a local copy of V8 or Node.js, you can really get a feel for what's in the language and what's not in the browser. JavaScript takes, in almost every environment, takes a lot of its identity from the standard library that it's been wedded to. And in most cases, because it has a very small standard library, all of that is in the environment. And so the more you can sort of remove those potential hurdles or sort of impedance mismatches with what's just in the language, I think the faster it'll help you learn it. Yeah.
And actually, in a similar situation as the previous question, which is I stayed away from JavaScript for a number of reasons. Probably one of the biggest ones was the lack of debug support. Mm-hmm. And the fact that you have unexpected surprises, like being able to overload the array constructor that lend itself to, security holes, whereas someone coming from another language isn't expecting that, and they don't even consider that as a possibility when you're looking at code. So specifically, is there anything that's talked about being added where, when you talk about modules, that the module can set up certain preconditions? I'm expecting these sets of things to be true, like the array constructor to not be overloaded, or anything else where you can say, flag, this is going to be a problem, we're not going to run right.
So one of the big things that's happening with the module syntax is that we're removing the ability to share globals. So you won't have a single shared global, which is going to be big to prevent people from sort of blowing your own legs off. The other thing is that ECMAScript 5, which the version that was just recently ratified, implements what we call a strict mode. And strict mode turns off some of the worst foot guns. It helps keep you out of trouble by giving you more and more pre-checking for things like uninitialized variables, that sort of thing, where it keeps you from sort of tripping over yourself in some pretty common areas. It's not perfect, but it's certainly a start. So use strict inside of all of your functions, and you should be good to go.
And what about the idea of official debug support?
So that's an engine-by-engine thing. The topic of common stack traces has been raised a bunch of times, and it's going to be very difficult because that constrains our ability to optimize. So things like eliding away dead code, those are the sorts of things that are going to be hard to do if we have to agree on a stack trace format. So what we do have is really good support, say, in the Chrome Web Inspector for setting breakpoints, future breakpoints, getting call stacks, and soon the ability to sort of wire up line numbers to source code. So yeah, debuggability is a hot topic. It tends to happen through the browser and not through the language runtime. So the question was, will the Clojure compiler help with debuggability? The Clojure compiler has Oh, will the Clojure compiler help beginners? No. It's designed to help folks who know that they have a problem avoid having problems. OK, cool. Thanks again for coming, and looking forward to it.